Let us discuss stacking faults in cubic close packed crystals. Stacking faults are two-dimensional defects, that is the surface defect, a kind of surface defect, 2D or surface defects. And the cubic close packed crystal or the CCP crystal, by CCP crystal we mean we have an FCC lattice. Any crystal is a lattice plus a motif, so FCC lattice, and the motifs consist of a single atom, one atom motif located at the lattice point, that is the displacement coordinate with respect to the lattice point is OOO. So let us look at that. Let us draw a simple unit cell. So FCC means the lattice points are at corners of the cube. This is a unit cell of the FCC lattice. Lattice points are at the corners as well as at the centers of all six faces. So top and bottom, left and right, and front and back faces. So the centers of all six faces. These are the lattice points. And when I say one atom motif, I mean that there is a single atom sitting at each of these lattice points. So let us place one atom at each lattice point. I'm drawing slightly smaller atoms. Actually, atoms are large enough to touch along the face diagonals of this cube. So these are the atoms. Now, in this crystal, if we consider this crystal can be considered as a stacking of close packed planes. Stacking of close packed planes. So let us show a close packed plane. A close packed plane in this, if this is x, y, and z. So 111 plane, 111 kind of planes are the close packed planes. So let me try to draw that. One along the x-axis, one along the y, and one along the z-axis. And the atoms which are lying on this plane are these three corner atoms and these three face centering atoms. The left face center, the bottom face center, and the back face center. So if I draw this now in plan here, so it's an equilateral triangle because all three sides are the face diagonal of the same cube, so they are equal, and there are atoms lying on the corners and on the edges of this triangle. Really, if you see, a better drawing will be to show them touching, because along the faces this plane is the same plane which I have drawn here. So you can see along the face diagonal they are touching. Now a given closed packed plane can be considered as an A plane. So I call all these atoms A atoms and the plane an A plane. The next plane above this will go at a location either B or C. And where is this B? The B is located in one of these triangular crevices. So let me call that location B. So this will be B, this will be another B, and this will be another B. So these are the B location. And third kind of location is the C location there. So the next layer of atoms will come in the B location, and above that again atoms will come in the C location. So the FCC lattice plus one atom motif giving you the CCP crystal is considered to be an ABC stacking of close packed plane. So I show it here. You can see I have written the stacking sequence of what you will see in a perfect cubic close packed crystal: ABC, 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 and ABC, so on. It will go on in both the directions. So a small portion, only 12 planes I have shown. A crystal will of course will have thousands or millions of such planes. Two kinds of faults are distinguished in cubic close packed structure: intrinsic stacking fault and extrinsic stacking fault. And we will try to create both of them now. So let us look at the intrinsic stacking fault. So let us say that this was a perfect stacking sequence. If there is some problem, some mistake, some fault, some error in this stacking sequence, that is what is called a stacking fault. So let us say we are going just like we are going for the perfect crystal ABC, ABC, but let us say one C plane is missing. In the imperfect crystal, one C plane is missing. So I have ABC, AB, C is missing. Instead of C, the next plane A comes. So ABC, AB, here we have A, and then again AB, C, ABC, and so on. So you can see that for a perfect crystal, ABC stacking sequence was required, but now in the imperfect crystal, or the crystal with defect, imperfect crystal containing an intrinsic stacking fault is what we have created. Where is that stacking fault? So let us say ABC, AB. I was expecting a C plane there, but that is missing. So ABC, AB, there is a missing C plane there. Missing C plane. So if a plane is missing, we call that an intrinsic stacking fault. You can see that the fault plane, so this itself is the fault plane, the plane between a B and A plane here, where a C plane is missing, is the plane of the fault. So up to that plane, if we look below that plane, ABC, ABC, AB. So this was a perfect CCP. There is no problem there. If we look above, so again we see ABC, ABC, ABC. So this is also a perfect CCP. There is no problem. So above this plane, I have a perfect crystal. Below this plane, I have a perfect crystal. However, if I cross the plane, I don't get the stacking sequence which I should see in the perfect crystal. So I have ABC, AB, there is a problem there. C is missing. So I have created an intrinsic stacking fault. It's called intrinsic because the missing C plane is not an atomic plane, and on either side the crystals are perfect right up to the fault plane. So the fault plane is not an atomic fault plane is not an atomic plane. Now let us create another kind of stacking fault. This time the extrinsic stacking fault. So in intrinsic there was a plane missing. In the extrinsic we will create one extra plane. So ABC, ABC. Now after C, A plane comes, but let us insert a wrong plane. After C, instead of A, I put a B plane. And then furthermore we carry on with, after C, A was expected, so I put it A, ABC, ABC, and so on. So you can now see this B plane is the fault plane. So now the fault plane is an extraneous plane of atoms. This plane is not part of the either crystal, because if you see ABC, ABC, A, I was expecting, if I am coming from below, the crystal below demands an A plane there, and crystal from above BAC, BA was demanding a C plane there. So this plane is not satisfying or is not part of either the bottom crystal or the top crystal. So that's why this is an extraneous plane of atom, and that's why this is called an extrinsic stacking fault. Extrinsic stacking fault, and fault plane is actually a plane of atoms. Is an atomic plane. We will look at one more interesting property of this intrinsic stacking fault, or rather another way of looking at the intrinsic stacking fault. Just now we saw for the intrinsic stacking fault, one of the planes was missing. So this is a perfect stacking sequence, and in this stacking sequence with an intrinsic stacking fault, there is a fault plane at ABC, ABC is missing, so there is this fault plane. Missing C plane is the fault plane. So how to think about this plane in a different way? We can see, rather than thinking of it as a missing plane, we can think that the plane above this, if I continue this here, plane above this, which in a perfect crystal should have been C, has become A here. So this means that C has shifted to A. C goes to A, and A has shifted to B. So A goes to B, and B has shifted to C. So B goes to C. So this kind of shifting has taken place. What is this shift? Let us look at. So again, if we draw the ABC stacking sequence which I had drawn, let us say that these are the A atoms, and the B location will be here, and the C location will be here. So when we say C goes to A, that means we are talking of this vector. So if I shift a C plane by this vector, a C plane will transform into an A plane. But you can see that the same vector will transform a B plane to a C plane because this vector is of the same length and in the same direction. And again, the same vector or a vector of same length and direction will transform A to B. So this A to A vector, this long vector, is divided into three equal parts: A to B, B to C, and C to A. Because B is a centroid of this equilateral triangle, C is centroid of that another triangle, and so this long diagonal of this rhombus is divided into three equal parts. This can be easily checked by geometry. This means that if this whole crystal, if this whole upper part of the crystal can be thought of as two parts, the upper red half and the lower green half. And if I keep the lower green half fixed and translate the upper red half by this vector, so I have translated it by this vector, and this vector is nothing but A to B vector. So A to B vector will take A to B, B to C, C to A, and so on. So this entire top half will be shifted and come to a new position, and this plane then will become a fault plane. So this is a translation interpretation, but the translation vector, this A to B translation vector, is not a lattice translation. Let us establish what this translation vector is. So remember, this is, let us relate this to our unit cell, the 1, 1, 1 plane which we had drawn. This is our 1, 1, 1 plane. So the atoms which I have drawn here, let me try to redraw them here. This is A, this is another A, this is A, and that is the back face center. So this rhombus is what I have drawn here. You can see. So you can see that this A to A vector is half the face diagonal here. So if I use my coordinate system, so this diagonal is -1 in the x direction and 1 plus 1 in the y direction. So this vector was -1, 1, 0 vector. So the AA vector is half of that. So this AA vector is half bar 1 1 0. Similarly, this AA vector, this one, is minus half along x and plus half along z. So this is half minus 1 0 1. So if we add these two together, this AA vector, the long AA vector, the red vector, this full length will come out to be the sum of these two vectors. So that is half 2 bar 1 1. And A to B vector, the A to B translation vector, then A to B translation vector is 1/3 of this half 2 bar 1 1. That is 1/6 2 bar 1 1. Thus we can say that the stacking fault, the intrinsic stacking fault in a cubic closed packed structure is equivalent to translating one side of the crystal with respect to the other side across a 1 1 1 plane by this vector. Of course, these planes, we know that 1 1 1 plane is actually a family of 1 1 1 plane, and similarly this direction is also a family of direction. For example, in this itself, I could have gone A to B this way, or I could have gone A to B this way also, or I could have gone A to B this way. So in a given plane there are 3 such vectors and there are 4 such planes, so there are many possibilities for this vector. So I can write this as a family of direction. So 1/6 2 bar 1 1. So this is the translation vector or the fault vector. Notice that this fault vector is not taking us from a lattice point to another lattice point, because B is not a lattice point in this plane. So in this closed packed plane, the A plane, B is actually a projection from another plane to this plane, but there is no atom located there in this plane. So B is not a lattice point. A to A will be the lattice point in lattice translation in that direction. So A to B is a non-lattice translation. That is an important point, because if it was a lattice translation, then of course there will be no fault created, because the plane will repeat itself and A plane will become the C plane. If translated by a lattice translation, will remain a C plane. So the fault is getting created because the translation is a non-lattice translation, and we have shown that non-lattice translation in the case of intrinsic stacking fault in CCP is 1/6 2 bar 1 1 kind of